So you can see this is the whatever diagram you are seeing, it is the fabrication step. So first one, you take a semi-insulating gallium arsenide substrate. Over that, you are going to grow the N-type region. Okay, and you are going to apply a photolithographic mask. Okay, so whatever region you want to uh, have it, you will be applying the mask. So for the other region, you will be implanting the N-type regions. Okay, the N-type region is ion implanted. So the mask எங்க இருக்கோ அந்த இடத்துல the implantation will not happen. Wherever there is no mask, there the implantation of N-type elements will be happening. So arrow mark indicates using ion implantation, I'm going to implant or dope the region with N-type material. Okay, and you can see here, now you have formed an N plus region where it is going to be heavily doped region consisting of large number of electrons, and you are going to have the remaining regions I am going to take for drain and source, correct? So I am going to dope those two regions. So now this N-type region will have a mask, and in between the three masks, you have two regions, right? So there you will be implanting the ions for fabricating your drain and source terminals. So this is a very lengthy process which is going to involve the it is going to involve everything. We'll see the text first. So the cross-sectional view of gallium arsenide D MOSFET is a depletion MOSFET is shown in the figure. So a thin N-type region joins the two ohmic contacts with a narrow metal Schottky barrier gate. Okay. So this is the thin N plus region which is going to form the metal semiconductor junction. Okay, it is going to form the metal semiconductor junction. In the process of fabricating D MESFET, the N-type dopants are directly implanted to form the channel and the more heavily doped source and drain. So you are going to directly dope the N-type N-type dopants using ion implantation method, so that you are going to form the source and drain terminals. Okay. So the gate and the first level interconnect metallization are deposited by the E-beam evaporation technology. The first one you see, I'm going to form the gate. The gate is formed first, then only I'm going to form the source and drain. The trans conductance of the device is determined by the gate position and the distance between the contacts. Trans conductance, it is going to be dependent on the gate length. So gate length is a very, very crucial role, and we know that for MESFET, the gate length was fixed to be 0.5 mm. You remember that it is 0.5 mm. So that is going to determine the parameters of D MESFET. So initially, the gallium arsenide substrate is coated with the first level of insulator, a thin layer of silicon nitride. So you see here, gallium arsenide is coated with a thin layer of silicon nitride, which is going to be an insulator. This thin film of insulator remains on the wafer throughout the processing steps and allows the annealing of temperatures up to 900 degrees. Why I am coating this silicon nitride insulator is this insulator will prevent any damage to gallium arsenide when I am going to heat the device at 900 degrees centigrade. That is the reason why I am going to have the insulating layer first. Then you are going to grow the N-type layer on the gallium arsenide substrate using ion implantation method. You see here, I am going to grow this N-type. I am going to grow this N-type region over the gallium arsenide using ion implantation method. Okay. It is semi-insulating gallium arsenide because I am using gallium arsenide plus silicon nitride as an insulator. So it is not a complete insulator. It is a semi-insulating gallium arsenide. So using this ion implantation method, uh, I am going to grow the N-type active layer. So the silicon nitride insulating layer is cut to make a window using photolithography for active implantation of N-type active layer. So you need to cut this layer. This is the above layer is going to be the silicon nitride, and some portion of the layer has to be cut so that you are going to apply the photolithographic mask. Photolithographic mask means wherever this mask is there, there will be no effect. The place where the mask is not there, you can grow the material. That is the logic. Okay. The implantation of the dopant ion takes place at a very high voltage to have an impurity concentration up to 10 power 12 per centimeter square. So it happens at a very high voltage because only at a very high voltage you can generate high velocity electrons, and these dopant atoms at that particular velocity will go and hit the surface and get implanted there. So these are the two main steps involved. There are two main steps involved: formation of a shallow N channel with high resistivity and deep N plus layers for source and drain. So two things I have to do with photolithography. One is I want to properly fabricate the N channel. Second one, I have to have two deep N plus layers for source and drain. You can see here, I'm going to fabricate the channel. This is going to be my channel, and I'm going to have N plus region, so that I will have two regions in between for fabricating my source and drain. This N plus will act like a gate, and in between the two gate and the other, in between on either side of both the gate terminals, you will be having the source and drain terminals. So the wafer is then coated with interleaved SiO2 by chemical vapor deposit, and this layer protects against any physical damage. You know, SiO2 we are using, and silicon dioxide is an insulator, and any damage is to the device is prevented using this coating of SiO2. So this step is followed by encapsulation. Encapsulation is important because it prevents out the diffusion of arsenic brought as a result of high pressure vapor when exposed to high temperatures. So at high temperature, arsenic may get diffused. So that is prevented by using this encapsulation of SiO2 layer. So you don't know at what temperature how the elements are going to behave, right? So for that, I'm going to make all the possible precautions in the fabrication. So the next step is formation of gates. So make contact in the first level metal interconnect. The metals must have very low contact resistance. Okay. So see here, you are having SiO2 insulation here, and then you see I'm going to use gold or germanium to create metallizing contact, so that when externally when you want to see the device will be having a structure like this. It will have a thing with three holes, that's all. It will have a thing with three leads. One is gate, one is source, and one is drain. And only when you use proper metallic wires to connect your terminals, gate, source, and drain, the device will work perfectly. Okay, that is what is mentioned here. The ohmic contact between the metal interconnect and the source and drain are deposited using E-beam technology, electron beam technology. So thin layer of gold, germanium, platinum alloy is used for contact. You know, metals are very good conductors. That's why I'm using metallic layer for the contact. And these metals should have a very low resistance. You know, the metals will have almost zero resistance, but whatever choice of metals you do, they should have a very low resistance because they should inject maximum current into the device. The following processes accomplish the first level metallization: delineating photoresistive patterns, plasma etching, the underlying insulator, deposition of the metal on the gallium arsenide wafer with sputtering, and the photoresist lift-off. See, photolithography, you will be using this mask, right? So whenever you have finished the process, you have to remove all those masks so that your actual device will be visible. So now you see you have a gate, you have on either side, you have source and drain, and you know that source and drain can be interchangeably used because they are identical. And in between source and drain, you'll be having the channel. And you have to cut out the unwanted remaining portion. That is done using all the technologies which we have shown, which we have discussed now. So delineating photoresistive pattern. So you are going to take out the photoresistive pattern which are not required. Plasma etching. Etching means you cannot, the size is very, very small, right? So you cannot remove it with your hand. So you have to use a plasma or vacuum to etch out the unwanted portions. Underlying insulator, deposition of the metal on the gallium arsenide wafer. So you want to have a metal contact to be established on the gallium arsenide layer, right? So for that you will be using sputtering and photoresist lift off, because everything is working in micrometer scale, correct? So you cannot physically do it with your hand. So you have to ensure that the process is going to be completely automated. So second level metallization entails a magnetron sputter titanium gold alloy, which is followed by filling the via between the first level and second level metal. The first level metal I'm going to use gold and gold, germanium, platinum alloy. Second level I'm going to use titanium gold alloy. And between the two metals, you are going to fill the via between the two metals. The final step is fabrication is the passivation and used to protect the water wafer from contamination. The final step is going to be passivation. Passivation means you're going to deposit a passivating layer at the low temperature using plasma enhanced CVD, chemical vapor deposition. So that will complete the fabrication of your D MESFET. And you can see here at the gate, you have a metal layer. At N plus region, you have a semiconductor layer. Between the two, you have a Schottky barrier gate. That is going to be the ohmic contact established. Same way between the source and N plus also, you have a metallic layer. Drain and N plus also, you have a metallic layer. All these are fabricated very, very carefully. So initially, you will have first level of gold, platinum, germanium alloy, and second level of metal you will be having titanium and gold alloy. The reason why we are using different alloys of gold is to ensure that when you establish a metallic contact with the semiconductor layer, so it is going to form an ohmic contact. That ohmic contact should be established perfectly, and that ohmic contact should produce a very, very, very low amount of resistance as the device is going to operate. Okay, so that is the reason for having so many minute details in the fabrication process of gallium arsenide. D, it is depletion MESFET. You know, depletion means whatever polarity you are going to give it to gate, exactly opposite polarity is formed. So whenever I'm going to give a negative supply to gate, here in the opposite side, I'll be forming a positive supply. So when you have more number of positive charges, my holes are majority, my electron is going to be reduced. So that is going to be the depletion MOSFET. In depletion MOSFET, the gate voltage will be negative. So that logic remains same throughout. So whether be it silicon or germanium or gallium arsenide, whatever be the material which is going to be fabricated, the depletion, whenever we are going to see about depletion operation of MESFET or MOSFET, we will know that the gate voltage has to be negative. Otherwise, when the gallium arsenide is going to be in enhancement mode, the gate voltage will be positive. So be very clear on how the operation of gallium arsenide is taking place in enhancement and depletion mode. So any queries on the fabrication, I'm going to pause for a few seconds. You can unmute yourself and ask. Okay. All these IC manufacturing technologies, whatever the processes, what we have learned, everything is automated. So the processing will go from one stage to another automatically, and there is no manual intervention required. And these, I don't think India we have an IC manufacturing fabricating facility, but in developed countries like USA, and where there is a very high scope for research, they have the companies have the dedicated fabricating facility where they will manufacture these devices at extremely uh, clean environment so that there no impurity is going into the device during fabrication. So that is ensured by the companies.